Now we know that orbitals are a region of space where there's a really good chance of finding an electron. We know that bonds are regions of space where we're sharing electrons between two atoms. And so we can see from all of that that the more that our two orbitals are overlapping, we're going to have a stronger bond, because there's a better and better chance of finding the electron in that region. So the more that we have them overlapping, the stronger the bond will be. But also the way that the orbitals overlap is going to tell us something about the bond order. Now we haven't talked about single bonds, double bonds, and triple bonds for a while, but this is where this is getting back to. Now, the first bond we're ever going to have is going to be an end-to-end overlap, and that's going to be a sigma bond. And that's the things we've talked about so far, where we have an orbital sticking out from one nucleus. We have another nucleus, and it's going to have an orbital sticking out. This is going to be a sigma bond, end-to-end overlap. Now that makes sense. That's the one we've always been showing in all of the videos for our AXE notations and also for the sp hybrids. It's all been end-to-end overlap. But can we have any other kinds of overlap? And for that, we have to think about the other orbitals that can be present on each of those central atoms. Now this end-to-end overlap, another thing I want to point out, when we call it a sigma bond, these are the first bonds that we make. These will always be the first bond you make. So for a single bond, it will always be a sigma bond. And the reason we chose sigma, when we were filling up orbitals on a lone atom, we first filled up our s orbitals, then we filled up our p orbitals. Well, here, we first fill up our sigma orbitals, then we'll fill up our pi orbitals. All right, so end to end, our single bond, this will be a sigma bond. Now you can see that being shown here. Now if we look at the atoms that we have here, we could come up with a Lewis structure for this. And I think that'll be illustrative as well. So we'll have a carbon, a hydrogen, and a hydrogen, hydrogen, and hydrogen. Now if we use our very fast rules for all of this, we get our single bonds in for everything. We know hydrogens only have one bond. We know carbons typically have 4 bonds. 1, 2, 3. So you can see that if we turn this into a double bond, 1, 2, 3, 4, 1, 2, 3, 4. Both carbons are now looking like they typically do. Now what we're saying is that we're going to have a bond between these two carbon atoms. Great. We have a bond shown, one bond so far, between our carbon atoms. So one of these is going to be our sigma bond. One of these is not. One of these is going to be something else, and we're going to describe it here momentarily. Now notice, though, we still have electrons up here and here, and over here. These electrons are there. Now if we count up the number of electrons on each of these carbon atoms, we're going to find that we'd have 1 electron here, and let's just say that we have 1 electron down here. Now you'll notice that I made this one an up arrow and this one a down arrow. I did that intentionally because if that's the case, remember these orbitals, we draw them like dumbbells because it's easier for us to visualize and easier for us to draw, but realistically they're a lot more like flattened out mushrooms. And even then, that was at maybe the 90% level. And if we go out to maybe the 95% level, the overlaps get even better. Not with as much likelihood, but they cover each other more and more. But notice that means that here on the top and the bottom, we have a pretty big region of space where we might have some sharing of the electron back and forth between these two atoms, aka a bond. Thing is, look at how wimpy that overlap is compared to end to end. That's why we make the distinction here. So the end-to-end overlap is what brought them together in the first place. Once they're together, that side-to-side overlap, if it's available, can create what we call a pi bond. So the second one is going to be a pi bond. And they look kind of like this. We have our 2 p orbitals. You see them overlapping like I was sketching up above. And you can see that it ends up making a giant orbital. Now both of these sides are parts of the same orbital. just like when we had our p orbital. Our p orbitals, oops, sorry, that was supposed to go to red. Here we are. This is one side, and this is one side of the same orbital. Our two electrons would be moving back and forth between both sides pretty rapidly. Same thing on this side. Well, the whole thing is a single orbital. We have one side high and one side low. So notice that when we have this, we're going to end up having this hot dog shaped s orbital here in the middle, and we're going to have this hot dog bun shaped orbital above and below it. That's going to be the second bond. Remember, the top and the bottom are parts of the same second bond. A third bond, if we had a triple bond, what we'd end up having is s orbital, p orbital, and we'd have another p orbital coming in and out of the paper. I'm just going to draw it like a disk here, and then I'll try to hollow it out a little bit. You can see that gets a little bit messy to try to draw by hand. That's what we're talking about for these orbitals. Our side-to-side overlap isn't as good as our end-to-end overlap, so the sigma bond is stronger than each of the pi bonds, which explains why, way back, we said our single bond is weaker than a double bond, but the double bond is not twice as strong. It's like 80% or 70 or whatever. It's less strong for that second bond, less strong for that third bond. When you add up all three bonds, the whole effect is bigger. Now, some people have a hard time remembering these, and I do like to have my ridiculous things that I do. I want to remind you that one of these will be kind of the temporary home of each of the two electrons. And I'll remind you of the names of all of these with my silly mnemonic. I'm bond, pi bond, but you can call me 00 sigma. So there you have a strange mnemonic.